For the item properties, we have order, flex shrink, flex grow, flex basis, flex align self. Yeah, here also flex attributes. Yeah, for the flex direction attributes, we have different values like row reverse, column reverse. Yeah, I said here, flex direction, this attribute is used to set the direction of the main axis. The arrangement or direction of the items can be specified by setting the coordinate axis. We have this syntax with 4 values of this flex direction. Row is the default value, and that means the main axis goes from left to right in the horizontal direction. So the items are arranged from left to right according to the main axis direction. For the row reverse, the main axis is the opposite direction of row, so it goes from right to left, and the items are arranged. Yeah, like the here say, the items are arranged from right to left according to the main axis direction. Then we have column. The main axis goes from top to bottom in the vertical direction. The items are arranged from top to bottom according to the main axis direction. Column reverse is the opposite direction of the previous one. So items are arranged from bottom to top according to the main basis and according to the main axis direction. Yeah, you see the effect here. Let's say, assume that we have 3 components, A, B, C, 3 projects. They are all same. Yeah, they are all the same in height and width. The effect of different values of flex direction is shown here. You see here, row, so from left to right, row reverse from right to left, column from top to bottom, and then column reverse from bottom to top. Then we have flex wrap attributes. You see here, this attribute is used to specify whether items are allowed to wrap and the direction of the wrap when arranged in multiple lines. We have a syntax format like here. Yeah, you see, if the flex wrap value is no wrap, it is also the default value. It means that there's no line breaks. If there is too much content in a single line, the width of the item may be compressed. If it is ripe, then when the container cannot fit all items in a single row, it can be arranged in a row. If it is ripe reverse, it means that when the container cannot fit all items in a single row, the items can be arranged in a new row, and the wrapping direction is the opposite of the wrap. We have the flex wrap attributes effect like here. Taking the horizontal direction as an example, suppose there are 4 components, A, B, C, D, 4 projects. All of them are the same in width and height. The schematic effect of different attribute values of flex wrap are shown like here. If it is a non-ripe, we'll put them all in our same row. If it is a ripe, we can change the row. If it is ripe reverse, we'll put the second row above the first row. Then we have the property justify content attributes. This property is used to set the alignment of items in the main axis direction and to allocate excess space between and around items. Yeah, the syntax format is like this here. We have the container, then justify content attribute. We have different values. And flag start as our default value. Then we have flags end, center, space between, space around, and space evenly. For the flags start, as we said, it is the default value. It means that the items are aligned with the starting point. Yeah, of items are aligned with the starting point of the main axis, and there is no gap between the items. Then if justify content is set as center, it means that items are arranged in the center of the main axis, leaving no gaps between the items. If the value here is set as a flag end, items are aligned to the end of the main axis, leaving no gaps between items. If it is space between, then space between items is equal, and the distance between the first and last items is 0 from the start and end point respectively. If it is space around, it is similar to space between. The difference is that the distance between the first item and the start point of the main axis and the end point of the last item is half of the distance between the middle items. If it is spaced evenly, it is distance between items. The distance between the first item and the starting point of the main axis, and the distance between the last item at the end point are all equal. Yeah, here are the achieved different values for justify content attribute. Then you see here, we have an example. If the horizontal direction is the main axis, assume that we have 3 components of project A, B, and C, and they have the same width and height. The schematic effect of different attribute values of justify content is shown here. You see, flex start is like this. We have no space between them. And then center, we have no space between them, and they are together. We put them in the center of the axis. If it is a flex end, it's like the opposite to the to flex start. Then space between, we have the same space between those projects, and the first project is begins with the axis, and the last project ends with the terminates. Then space around, it is similar with space between. And the difference is that here we have space between the first project and the axis, and the third, so the last project with the end of the main axis, we have a space, and both this space and this space are half of the space between projects. Yeah, this is space around. If it is space evenly, the difference between these two is that the space between the first project and and beginning of the axis, and the last project with the end of the axis, they have the same distance as the space between projects. Yeah, these are different. Yeah, these are different values of justify content. Another attribute is align items. We have 5 values with this attribute align items. You see, it can be stretch, which is also the default value. It can be flag start, center, flag end, and baseline. For stretch, it is also the default value. It stretches the item to fill the cross axis when the item size is not set. If it is flag start, the top of the item is aligned with the starting point of the cross axis. If it is center, the item is aligned in the center of the cross axis. If it is flag end, the bottom of the item is aligned with the end of the cross axis. If it is baseline, the item is aligned with the baseline of the line, which is equivalent to flag start when the baseline is not set separately. Yeah, you see here are these values of these align items attributes. Here we have an example. Yeah, in this example, we say that this vertical direction is the main axis, and we have 3 components of items A, B, and C. Each of them, has the Y's 200, 300, and 400 RPX respectively. And when the aligned items is set as stretch, then the Y's of the items could not be set. You see, with these different Y's, we have the effect like this. As we say, if it is stretch, we will stretch to the whole axis. And for flag start, we'll keep the start of these items with the cross axis as this part here you see. As A 200, B 300, and C 400. Then we have this, the align of these items like this, A, B, C. If this attribute is set as center, then you see each of them is set, is in the middle of the axis, like here. It is the center of this axis. Then the center, you see each item is set in the center of the axis. For flex end, it's the same, it's that like the opposite of flex start. We put the items at the end of the axis. So you see it is opposite to flex start. Then we have the align content attributes. The align content property is used when arranging multiple rows to set the alignment of items in the cross-axis direction and to allocate extra space between and around items. Here we have the grammatical format, like here. Yeah, you see, we have 1, 2, 3, 4, 5, 6, 7. We have 7 values for this align content. It can be stretch. This is also the default value. We have flex start, center, flex end, space between, space around, and space evenly. Yes, similarly, here we have the explanations of these values of this align content attribute. Stretch is the default value. When the item size is not set, the items in each row are stretched to fill the cross axis. And when the item size is set, the item size remains unchanged and the item line stretches to fill the cross axis. Yeah, you see here, stretch, it is nearly the same with other attributes. Like, yeah, here align content, before we have align items. Yeah. So you see, when we see the align items or align content, we can have this value stretch. Then we have flag start. It means that the first row is arranged at the starting point of the cross axis, and it leaves no space between the rows. Yeah, it is also the same, nearly the same as align items attribute. Flag start. Then we have center. That means rows are arranged at the middle point of the cross axis, and there is no space between the rows. The distance between the first row and the end of the cross axis is the same as the distance between the first row and the end of the cross axis. Yeah, here is the center. It is also similar with the align items. Yeah, you see here, rows are arranged at the middle point of the cross axis, and there is no space between the rows. So each row is set together. Yeah, the distance between the first row and the end of the cross axis is the same as the distance between the first row and the end of the cross axis. Then we have flex end. For the flex end, last row is arranged at the end of the cross axis, and it leaves no space between the rows. We have also space between. Space between, it means line to line spacing is equal, and the distance between the first line and the end point of the cross line from the first line and the end of the cross axis is 0. Yeah, you see, they begin with the cross axis. That's why we say the distance is 0 for the space between. Yeah, it's also similar with the align items. This is the space between. Space around, it is line to line spacing is also equal, and the distance between the first line and the end of the cross axis from the start of the cross axis and the end of a cross axis from the first line is a half of the line to line spacing. Yeah, for space evenly, sorry. For space evenly, it is spacing between rows and the distance between the first row and the end of the cross axis and the end of cross axis are equal. So you see, for multi-line arrangements, we set the flex wrap attribute value to wrap, and it indicates that line wrapping is allowed. Here we have an example. Similarly, we take the horizontal direction as the main axis. Here we have 5 components of project A, B, C, D, E with different Ys. And the schematic effect of different attribute values of a line content is shown here in this figure. Here, this one is line content. You see, when we set it as a stretch, they are stretched with the cross axis. If we set it as flex start, they are like this. It starts from this axis. If we set it as a space between, it's like this. We have space between them, and the first project is closely connected to the axis, and the last project is closely connected to the end of the cross axis. For space around, we have space here and here, and this space is half of the space between projects. And then for center, they are altogether. It's similar with flex start, just we put them in the middle of the cross axis. For flex end, it's the opposite of flex start. You see, it's the opposite. For space evenly, it is similar with space around. Space around the space here and here, they are half of the space between projects. Here, for space evenly, all spaces here, they are equal, they are same. So here we have explained the values of this align content attribute. Now we will see other properties. First of all is the order attributes. The order property is used to set the arrangement order of the items along the main axis. As seen here, the smaller the value, the higher the arrangement. And the attribute value is an integer. Its grammatical format is like here. It's given here. And 0 is the default value. So normally, it means it is the most prioritized. Here we have an example. In this example, the horizontal direction is the main axis. You see here, it is the main axis. We have 3 components of project A, B, and C. All of them are the same in width and height. You see here, the schematic effect of different attribute values of order is shown here. Project B is set at, the order of it is set as -1. C is 2. A is 6. As we say, the smaller is the order. It is more prioritized. Prioritized. So here, -1 is the smallest. So this is the first one. Then with the order 2, this one. Then order 6. You see the order. -1 to 6. That's the order of it. Then we have the attributes flex shrink. Yeah, okay. This one is a bit difficult to understand here from here. The flex shrink attribute, it is used to set the item shrinkage factor. When the item overflows in the main axis direction, the item is comprised by the specified ratio of the item shrinkage factor to fit the container. The syntax format is here. Yeah, you see, we use flex shrink to set the shrinkage factor of the project, and it can only be a non-negative number. Yeah, here we have formula. When overflow occurs, the shrinking formula of the item size is like here. We have the final length, which is the original length times this factor. This factor, yeah, in the case of decimals, it is rounded down instead of rounding. So you see the formula for calculating the total weight of compression is as here. Yeah, we have the total compression, which is each length times each shrinkage factor. So when the main axis is from left to right, the length refers to the width. When the main axis is from the top to the bottom, the length refers to the height. Yeah, take care these formulas. We'll use them in this example. Here we have an example. In this example, the horizontal direction is the main axis, and we have 3 components of project A, B, and C, each with a width of 200 px. Set the shrink factor of the project to 1, 2, and 3 respectively, like here. You see, you see here, support, okay. I will ask you to do it, perhaps. Support the width of the container is 500 px. And then as here we have, yeah, we have project A, B, and C, each with a width of 200 px. We have the shrink factor of each project. So calculate. The final width of each project after shrinking. Okay, is it clear?
Yes, Laoshi.
Okay, thank you. Roy? How have you, Kaya, how have you calculated the 250 and the 166? Dividing the shrink value provided 2 and 3. Oh, how about A? Project A. Oh, you see here, we have a container. The width of the container is 500 px. And we have 3 projects, A, B, C. The width of each project is 200. So each project should shrink with the shrink factor. Okay. Here you talk about this one, total compression weight. Here, shrinkage factor, they are just adapted to different items, not for the container. You see, container is to contain, is to support those items. So you don't need to add the container there. Okay? Is it clear? We have a container. We need to put those items there. The container and the size of it is limited. So we need to shrink those items to put them in the container. We don't need to shrink the container. Am I clear? Here, this formula is adapted to those for those items in the container. The container, we don't need the, we don't need to shrink the container. Is it clear? Okay.
Wait, Lasha, I'm a bit confused again. So we don't need to shrink the containers themselves. We need to shrink the overall screen, right, Lasha?
Yeah, when the container, we don't need to shrink. We need to shrink those items or those projects, as we need to put those items in the container.
So so basically we'll say 200 times 1, 200 times 2, 200 times 3, right, Laoshi? And then since we're not shrinking the container, we're just shrinking the projects, that'll be our total compression weight.
Yeah, exactly.
Okay. But what's the overflow length again, Laoshi? That's
Pardon?
the 500 px, the overflow
Yeah.
length.
Yeah, the container. Yeah, the width of the
Okay.
container is 500 px. Oh, sorry, I didn't see here this one. Here is like this, but the final here, you see final length is also for each item.
So I need to say 200 so I need to calculate the final length for each project, right, Laoshi?
Yeah,
For each
exactly.
method.
Yeah, yeah. Yeah, perhaps we can have a break of 10 minutes. Yeah, if you want, we can continue and we terminate 10 minutes before. You see what I mean? Do you want to have a break or not?
No need for break, Laushi. We can continue.
Okay, thank you, Roy. Yeah, you see here as Sepkaya, we need to calculate for each project or each item. Okay, thank you, Kaya. You mean here is the original length, and then it multiplies by 1 minus overflow length. Yeah, here is the total compression weight. Then first, you mean, so you consider the overflow length as the width of the container?
Yes,
Perhaps.
Laoshi.
Overflow length, it is yeah, it is the needed, we can say needed length minus the container width. Yeah, the needed length is the yeah, if I write it like this, it is clear. The needed length is the sum of original width of projects or the original width of items. It is the total, the sum of them. Yeah. Yeah. And pay attention here. We don't have a parenthesis between here and here. So you need to firstly calculate the multiplication between overflow length and shrinkage factor. Then this part, then we divide, this result by total compression weight. At last, we do the minus. Yeah. Oh, sorry, Kaya. How you get the overflow length at 400?
So the overflow length will be the needed length, which is 200 plus 200 plus 200, which is equal to 600, minus the container width. The container width in each instance is 200, right, Lao Xu? That's how I ended up getting 400.
No, container OIC is here, you see.
Oh,
Suppose
500.
the width of the container is 500. Yeah.
Oh, I'm confusing it with the other. Okay, okay, I understand now, Lao Xu.
Yeah, okay. So you can recalculate it.
Is this okay, Lao Xu?
Yeah, perfect. Yes. As given by Kaya, here we got the length, the one, yeah, the final length of project A as given by yeah, I argued directly. Yeah, you can check it. Here is the width of each project. Yeah, you see, given here. As we say here, assume that the width of the container is only 500 px. The px, the sum of the three item is 600 px will obviously overflow 100 px. So the contraction pixels. Yeah, the contraction factor is triggered to compress the width. First, the total weight of the compression is calculated like this. We have the compressed total weight calculated as this. When overflow occurs, the shrinking formula of the item size is like this. So it can be seen that the original project components of the same width have different widths after compression due to different compression factors. Yeah, you see when the compression factor is 1, we get wider project. When it is 3, we get narrow project. So it is proved that the larger the compression factor value, the shorter the compressed length. Yeah, you see here. The schematic effect of this example is here. Yeah. The original IC is 200 pixels. And here we have 100 overflow. And after calculating, we get the final width of each project. We get these 3 projects. So you see, it should be noted that only when the sum of the first flex shrink attribute values of the item shrinkage factor is greater than 1, the overflow length is calculated according to the actual situation. When the sum is less than 1, the conversion formula of overflow length is like here. Yeah. For example, if the flex shrink attribute values of items A, B, C in the previous example are updated to, instead of 1, 2, 3, if it is 0, 1, 0, 2, 0, 3, then the sum of these shrinkage factor is 0, 6. It is less than 1. So the overflow length is calculated like this. Yeah, and then we use this to replace 100. Okay, this is flex shrink. Then we'll see another attribute, flex grow. Flex grow properties are used to set the project expansion factor. When the project has remaining space in the main axis direction, the remaining space is allocated by setting the project expansion factor. We have the syntax like this, flex grow, and its attribute value is the expansion factor of the item, which can only be a non-negative number. Here, when we have expansion, we have a formula to calculate the expansion, the project size, like here. Final length is given by the original length plus expansion unit times expansion factor. And we should pay attention that in the case of decimals, it is rounded down instead of rounding. Yeah, here we have another formula to calculate the expansion unit. Yeah, you see expansion unit is, it's calculated like this, and we will replace it here, expansion unit. This expansion unit is the remaining space divided by the sum of the expansion factors. So you see, when the main axis is from left to right, the length refers to the width, and when the main axis is from top to the bottom, the length refers to the height. Yeah, pay attention to these 2 formulas. We'll calculate them with our examples. You see here, we have an example. We take the horizontal direction as an example. Suppose we have three components of project A, B, and C. And each component has a width of 100 pixels. The expansion factor of project A, B, and C are 0, 1, and 2 respectively. Then we calculate, then we need to calculate the width of project ABC at the end. You see here, we have project ABC. Each of them has a width of 100 pixels. And the expansion factor of them are 0, 1, and 2. Then calculate, okay, support the width of the container is 600 pixels. Calculate. The final width of each project.
Now, how do you get the remaining space?
Pardon?
How do you calculate the remaining space?
Here, I'm sorry.
Yes, for the expansion unit.
Yeah, you see, remaining space, it is the container, the width of the container minus, like before, minus the space, the needed space, the needed length.
Okay. Well, this is kind of how we calculate the expansion units.
Adam? Yeah, okay, thank you. You see, you give this one, expansion unit, it is the remaining space divide by the sum of expansion factors, not just the sum of the width.
Oh, the expansion factor. Okay.
Yeah.
So the expansion factor is 1, 2, and 3 respectively, right, Laoshi?
Yeah.
So this is our
Exactly.
expansion unit.
Yeah.
Okay.
Perfect. And then you can continue.
Yes. The original length is the main length, the 600, right, Laoshi?
No, now like our previous example, final length we need to calculate them for each. Yeah, we need to calculate final length for each project,
Yes.
and the original length is the original width of each project.
Oh, okay. Okay.
So you have, thank you, Kaya. You have given how you get 200 here. How you get 200 here?
Oh, I forgot that it's 100. It's one.
Yeah,
I was using the width from the previous one. Sorry. Okay.
don't worry. Oh, I'm sorry. I'm sorry. I forgot one thing about it, that it doesn't matter. Okay, it's okay. Yeah.
Okay. Now.
Yeah, you can. So just you replace here by 100. That's all. Yeah.
Yes, Aoshi.
Okay. Thank you very much, Kaya. You got it. Yeah, you see here. With my slide, I have put instead of 1, 2, 3, I have put 0, 1, 2. So you will see it's different.
Oh,
Yeah,
okay.
0, 1, 2. The expansion factor I have set as 0, 1, 2. So the expansion unit is calculated differently. Assuming that the container has a width of 600 pixels, the sum of 3 item width of 300 pixels will obviously exceed the remaining space of 300 pixels. So the expansion factor is triggered to expand the width. First, the expansion unit is calculated as this. We have the remaining space, we divided by the expansion factors 0, 1, 2. So we get 100 pixels as the expansion unit. Then we allocate the remaining space to the project wise. The new project wise expansion formula is like this. We have the original length, the expansion units, times expansion factors. So we get them like this. Yeah, it can be seen that the original project components of the same width have different widths after expansion due to different expansion factors. And it is proved that the larger the expansion factor value, the longer the expanded length. And we have here the schematic effect of this example is shown here. The original effect is like this. We have A, B, C, 3 projects. We have the remain space like here. Then after expansion, yeah, we have then like here. Yeah, you see, at first they have the same width. As they have different expansion factors, their final widths are different. Yeah, here is for this attribute, flex grow. As saying here, it should be noted that only when the sum of the flex grow attribute values of the item expansion factor is greater than 1, the expansion unit is calculated according to the actual situation. And when the sum is less than 1, the expansion unit is the total remaining space. For example, if the flex grow attribute values of item A, B, C in the example are updated to 0, 1, 0, 2, 0, 3, it respectively, and the sum is 0, 6, less than 1, the expansion unit is 300 pixels. The subsequent calculation is exactly the same as the previous formula. The fourth attribute we'll introduce here is the flex basis attribute. This attribute replaces the width or height of the item according to the main axis direction. The specific explanation, we have them here. When the container sets the flex direction to row or row reverse, if the flex basis and width properties of the item have values at the same time, flex basis will replace the width property. Yeah, you see here is there. Yeah, we have already seen flex direction with row and row reverse. And this another explanation is that when the container sets the flex direction to column or column reverse, if the flex basis and height properties of the item have values at the same time, flex basis replaces the height property of the item. That means, yeah, according to these explanations, flex basis has higher priority. Here we have the syntax of flex basis here. It should be noted that the numeric value has a higher priority than auto. If the flex basis attribute value is auto and the width or height attribute value is a numeric value, the numeric value is used as the final attribute value. As seen here, we have the priority, different priorities. Here we have an example. We take this direction as the main axis. Suppose we have 3 components, A, B, and C, with a width of 100 pixels. Yeah, we add a flex basis value of 200 pixels for A. The final schematic effect will be like this. Yeah, we can see that the width of item A is wider than B and C. This is because the flex basis priority is greater than width. So if the value of flex basis and width or height, if they are different, yeah, we base on flex basis instead of width or height. Here we have flex attributes, which is shorthand for flex grow, flex shrink, and flex basis. Here we have the syntax. We set the attribute value to none, which is equal to 0, 0 auto. And setting to auto is equivalent to 1 auto. Here is flex attribute. Then we have align self attributes. The align self attributes sets the alignment of the items in the cross-axis direction of the row, and we use it to cover the aligned items of the container. And yeah, this can be done to deal with the alignment of the items. Here we have the syntax. The default attribute value is auto here. It means that the align items value of the inherited container. If the container does not set the align items attribute, the default value of align self is expressed as JEDGE. Yeah, refer to the explanation of align items for other attribute values. Yeah, here we have another attribute, align self. Here we take the horizontal direction as an example. Suppose we have 4 components of items A, B, C, and D. A, B, C, they have the same y-san height. D does not define the height and the schematic effect of different attribute values of align self as shown here. Yeah, you see here are these attributes for flex model. Yeah, here what is important is to know this part. The shrinkage and the expansion. Yeah, it is important to calculate these, the shrinkage and the expansion. For the attribute flex shrink and flex grow. Here, I'll give you some exercise. Taking the horizontal direction as an example, suppose there are 3 components, A, B, and C, each with a width of 300 pixels. Set the shrink factor of the project to 4, 2, and 3 respectively. Suppose the width of the container is 500 pixels. Calculate final width of each project. You see these two exercises?
Yes, Laoshi.
Okay, thank you, Claire. If you want, I'll set them as the assignment and we'll do some other revision here. Yeah, I have set our assignment. I'll have set them as assignments. Then we'll revise these things differently. For example, for the flex direction attribute, what values are possible? We have talked about this during this lecture.
Column,
Yeah, yes.
Row.
Yeah.
Yeah, column, row, reverse. I already said reverse.
Yeah, thank you, Kaya and Roy. Yeah, we have these four values. Row reverse, column and column reverse. They show different display of items. Yeah, these things, in fact, these attributes, they may be, they may be useful when you write project. Yeah, when you do real projects, they may be very useful. Flex, right? How about this attribute? Yeah, and we have already explained, we have already explained for what Kaya and Roy has said the flex direction attribute. Row is from left to right. Column is from top to bottom. Row reverse is from right to left. Column reverse is from bottom to top. And how about this attribute, flex right attribute? Yeah, thank you, Roy and Kaya. But Kaya, I think you have confused it with justify content. Yeah, perfect, Roy. Yeah, we have 3 values: ripe, ripe reverse, and no ripe. Yeah, Kaya, you have yeah, you have thought about justify content. For this attribute, we have center as as a possible value. Also align items and content. I think also, align content. For those 3 attributes, we have center as a value. Yeah, for justify content, we have flag start, flag end, center, space between, space around, and space evenly. For align items, we have stretch, flag start, center, flag end, and baseline. Yeah, similar for align content. Okay, are there any questions? Do you have some questions?
No, 老师。
Thank you,
那
Kaya.
老师。
Thank you, Roy.